All right, if you're getting ready for a big exam or, say, a PhD defense, and you need to be an absolute expert on aerosol technology, you are in the right place. Today, we're tearing down Chapter 4 of Heinz Aerosol Technology. We're going to focus on the statistics of polydisperse aerosols. The goal here is to build a rock-solid understanding of these concepts, one that you can really defend. Let's jump right in. So, right off the bat, here's the big problem. An aerosol isn't just one thing, right? It's a whole cloud of particles, and their sizes can be all over the place, spanning huge ranges. If you just list out a million particle sizes, well, that's not useful to anyone. We need a smarter, more powerful way to talk about the entire population of particles. So here's how we're going to tackle this. First, we'll really nail down the core problem. Then we'll see how we can wrangle all that raw data into something useful. We'll explore the idea of average and see it's not as simple as you think. Then we'll hit the big one, the critical difference between count and mass. After that, we'll introduce the log normal model that kind of ties it all together, and we'll finish up with how to actually use it. And a really important warning. Okay, section 1. The core problem really boils down to this. You have this massive range of particle sizes, and that makes any simple description basically impossible. We have to use statistics to find the pattern hidden in all that chaos. I mean, really, think about that. If someone asks you to describe an aerosol you've been studying, are you going to hand them a spreadsheet with thousands of rows of particle diameters? Of course not. That's useless. We need tools that can summarize all that information, that can capture the real essence of the distribution in just a few key numbers. So, how do we begin to tame this mess of data? Well, the very first step is to bring some kind of order to it, to turn that endless list of numbers into something we can actually see and understand. We start by grouping the data. We create these little intervals, or bins, and then we just count how many particles fall into each size range. This turns our long, messy list into a nice, clean table. It's definitely a step up, but it's hiding a pretty serious flaw, one that can really mislead you. So you take that table and you plot it as a simple histogram. And here's where the problem shows up. See how the bars have different widths? A wider bin is naturally going to catch more particles, just because it covers a bigger range, so its height makes it look more important than it really is. This is not a true picture of the distribution at all. It's distorted. And here's the fix. It's so important. To get a real, honest picture of what's going on, you have to normalize. You just take the count in each bin and divide it by the width of that bin. This one simple step is the absolute key to creating an accurate picture. And boom, here's what you get. Look at the y-axis now. It's count per micron. It's a density. In this corrective view, it's the area of the bar, not just the height, that tells you the number of particles. Now we're talking. Finally, we can compare these different size ranges fairly. This is the true shape of our data. Now imagine if we could use a crazy number of incredibly tiny bins, and then we just connected the dots. What we get is this beautiful, smooth curve. This is the frequency distribution. It's really our ultimate goal, a mathematical function that perfectly describes how our particles are spread out by size. And the total area under this curve, it's always 1, representing 100% of our particles. Okay, so we can see the distribution now. But how do we describe its center? You might just say, let's find the average. But in statistics, and especially for skewed distributions like we see with aerosols, the word average can mean a few very different things. Let's break these down real quick. The mode is easy. It's just the most common size, the very peak of our curve. The median is the 50th percentile. It's the size that splits the number of particles perfectly in half. And the mean is your good old arithmetic average. Now here's the key. For these skewed aerosol distributions, these three are not the same. The mean gets pulled way up by those few big particles. So you'll almost always find that the mode is the smallest, then the median, and then the mean. Remember that order. Now, things get a little more advanced when we start talking about moment averages. Basically, a moment in statistics is just a way to describe the shape of a distribution. But for us, it's a powerful way to connect the number of particles to physical things we actually care about, like their total surface area or their total mass. Since those things scale with diameter squared or cubed, averaging them gives us these really useful descriptions. Okay, let's move on to what is, without a doubt, the most important concept to master in this entire chapter. If you're building a defensible argument about your aerosol data, understanding the massive difference between a distribution by number and a distribution by mass is absolutely non-negotiable. This quote from the book is the single best analogy you will ever find for this concept. It is perfect. It just instantly makes the whole idea click. Let's actually see what this looks like. So, if we're just counting items, it's dead simple. There are 10 things in the bowl. 9 of them are grapes. So, 90% grapes. By count, this bowl is overwhelmingly full of grapes. But now, look what happens when we change our perspective to mass. That one heavy apple totally dominates the system. The tiny grapes barely register. The whole distribution flips on its head. This is exactly what happens with aerosols. A handful of very large particles can hold almost all of the mass, even if there are thousands of smaller particles outnumbering them. So we formalize this idea with 2 key parameters. The count median diameter, or CMD, is the median based on the number of particles. But the mass median diameter, or MMD, is the median of the mass distribution. It's the size that splits the total aerosol mass right in half. And just like with the grapes and the apple, the MMD is always going to be bigger than the CMD. So with all these different ways of looking at things, is there a mathematical model that can help us make sense of it all? A way to easily switch between count and mass? Thankfully, for most aerosols that come from a single source, the answer is yes. It's called the log normal distribution, and it's an incredibly elegant and powerful framework. Here's the deal. A distribution is log normal if, when you plot it against the logarithm of the particle size, you get a perfect, symmetrical bell curve. And this is amazing, because it means we can describe the entire complex distribution with just 2 simple numbers, the count median diameter, the CMD, which tells us where the center is, and the geometric standard deviation, or GSD, which tells us how spread out it is. And this is the superpower of the log normal model. For any given aerosol, it's not just the count distribution that's log normal. The distributions for surface area and mass are log normal too. But here's the magic part. They all share the exact same GSD. They all have the same spread, the same shape. They're just shifted to different points along the size axis. This is the key that unlocks everything. Because they all share the same GSD, we can use this really powerful toolkit for converting between all these different properties. But, with great power comes great responsibility. We have to be super aware of the model's limitations. These are the Hatch-Choate equations, and we can think of them like a simple toolkit. There's a single formula, and if you want to convert from your CMD to any other average diameter, like the MMD, you just look up the right value of B from this table, plug it into the formula with your known CMD and GSD, and you're done. It lets you measure a number distribution, for example, and then calculate what the mass distribution must be. But here is the final and most crucial warning. As this quote says, the mass distribution is dominated by the biggest particles. And where are those particles? They're the rare ones, way out on the tail end of the number distribution. So if your instrument didn't do a good job of accurately measuring those few giant particles, any MMD you calculate is going to be garbage. And this, right here, is the difference between just applying a formula and being a true expert, knowing that your model is only as good as your data, especially the data out on the tails. Nailing that nuance is how you truly defend your results.